Okay, today we're going to talk about quantities of heat. There are two different equations to calculate the amount of heat. One way is using calorimetry, where we're heating and cooling, meaning we're changing the temperature. We use Q equals mc delta T. When we have the heat of a phase change, though, we don't have a change of temperature, and so we use Q equals mass times heat of vaporization. We use heat of vaporization when we're going between liquid and gas. And we use heat of fusion when we're going between solids and liquids. So let's review the variables. Q is the quantity of heat. And the unit that we use for heat is joules. We can also use kilojoules, but in these two equations we're going to use joules. M represents mass, and we measure mass in this case in grams. C is the specific heat. You will sometimes see specific heat written as C or sometimes as CP, like a subscript P. And the units for that are joules per gram degree Celsius. And then finally we have delta T. This delta means the change. So this is change in temperature. And to find the change in temperature, we always do final minus the initial. And we measure temperature, in this case, in degrees Celsius. Now the heat of the phase change. Q, again, is still the quantity of heat. So its unit is still joules. M is still mass, measured in grams. And H is the heat of vaporization, which is the heat required to change something from liquid to gas. And heat of fusion is when we go from solid to liquid. Now we can use the reverse of those, and when we do the reverse of those, we just change the sign. Okay? So the reverse, the opposite direction would be negative, because those would be exothermic. So C for liquid water, these are our special constants we need to know for water. Specific heat of water, ice, and steam we will need in order to do problems using Q equals mc delta T. These you can find on your reference tables that I gave to you on the first day. Right? And you can see here specific heat of water. Right? CP, you see there, and it tells you for ice, steam, and liquid water. So you can write these down in your notes, but you also know that they are listed here, so you do not have to memorize them. Likewise, heat of fusion for water and heat of vaporization for water are also here in your reference tables. So you take a second and write those down in your notes. Alright, so let's review. We're going to use Q equals mc delta T when we have a change in temperature. Okay, and we're going to use the heat of the phase change when we have no delta T, which means we have a phase change, such as melting, freezing, boiling, condensing. Again, review a positive amount of heat. Q is the quantity of heat, so a positive heat means we have an endothermic reaction or process. And a negative Q means we have an exothermic process. So let's look at a heating curve again. If you recall, we start as a solid, and then we melt, and then we have liquid, and we change the temperature of liquid until it will boil, and then we would have gas or steam if we're talking about water. And remember, this axis is your temperature in degrees Celsius, and this, of course, is our energy in units of joules. Now again, we have in this region a solid, and then in this region is when we're changing from solid to liquid. In this middle region we have a liquid, and in this flat region we're going from liquid to gas, and then finally in this region we have gas. So in the first region here where we have solid, it's changing temperature, right? Right here this would be 0 degrees C. We're talking about water in this case. Okay? So anywhere along this first segment where it's all solid, we would be changing the temperature. And so in this case, we would be using our equation with our delta T. What I'm going to do is number the equations. We're going to call this equation number 1. We're going to call this equation number 1 and this equation number 2. Okay? We're going to make a key here. Equation 1 is Q equals mc delta T. Equation 2 is going to be Q equals mH. Alright, so in the first region we have a change of temperature, and so that's going to be equation 1, Q equals mc delta T. And in the second phase here we have a plateau. Our temperature remains the same. This is because we are increasing our potential energy, we're decreasing our potential energy, we're converting it more to kinetic energy. And so in this region we're changing the state of matter. Here we are melting. And since we are melting, we are going to be using the equation Q equals mass times the heat, in this case of vaporization. Heat of fusion, because we're melting. And then in this region, we're going to again have a delta T, so we're changing the temperature. And so we're using equation 1 again. Now in this next region, we have a plateau again. So we're changing from liquid to gas. Again, this is a phase change. This one we would call either boiling, or we could also call it evaporation. Right? And so again, since we have no delta T, it's flat, right? And to review, this occurs at 100 C for water. Right? So we're boiling, and we're going to use then the equation Q equals mass times the heat of phase change. So this is the second equation. And in the second equation, in this case, since this is vaporization, we're going to use HV. Vaporization to make into vapor, right? And so finally we have a change in temperature of our gas, and so we're going to use equation 1. Alright, so let's look at some problems, some instances of where we'll use this information. Alright, so we can do a process called calorimetry. Calorimetry is just a process where we can determine a change of temperature of a substance. And so according to the law of thermodynamics, okay, which in this case we're focused on conservation of energy, heat cannot be created nor destroyed, right? We talked about that before. We talked about how we can transfer it or we can convert it. So we talked in the heating and cooling curves about converting it. In this case we're talking about transferring it. So if you put hot metal into cold water, what happens to the heat? So in order to understand what's going to happen to the heat, we know that heat flows from things which are hot into things which are colder. So the heat is going to transfer. And so in this case, what's going to gain the heat? Well, the cold water. And what's going to lose the heat? The hot metal. How much heat does the water gain? Well, remember, we have to conserve energy. So energy can't be created or destroyed. Right? We can just move it from one place to another, but we have to move the same amount of energy. So the water will gain the amount of heat that the metal loses. So what would be the final temperature of the water compared to the metal? So in other words, at what point do they stop transferring heat? Well, they stop transferring heat when they have equal temperature, because at that point they would have equal heat content. So when the final temperatures are equal is when that heat transfer will stop. Alright, so we can use this information to help us determine the specific heat of metals. Okay, that's when we would use this information. So we're going to look at a couple of different problems. First problem is looking at a heating curve. And we were just talking about a little bit ago, this curve here on the previous page, right? So in this case, we have 12.5 grams of water. We're heating it from 30 degrees to 50 degrees. So where would that be on our little graph? So it'd be right around from here, let's say to about there, right? Alright, so how much heat would be required to do that? Well, what state of matter is the water in at this point? It's a liquid, right? So we're going to need the specific heat for liquid water. So we find that on our reference table is 4.18 joules per gram degree Celsius. Alright, and so we want to know how much heat energy, and remember we talked about the amount of heat is the variable Q. Right? And we also know the grams, and so grams goes along with our variable M for mass. And so we can determine Q equals MC, and we do have a delta T, a change in temperature, right, measured in degrees Celsius. So we plug in this information that we know. Q equals the mass, which is 12.5 grams, times the specific heat, which is 4.18 joules per gram degree Celsius, times the change in temperature. Remember, the change in temperature is the final temperature minus the initial temperature. And so in this case, that would be 50 minus 30 would be a positive 20 degree change. Alright, so then we use our calculators and we multiply 12.5 times 4.18 times 20, and we determine the number of joules. So take a moment and calculate that amount. Right, and so we get 1,045 joules. Now, because we have to consider our significant figures, remember our answers can't be more accurate than our least accurate measure. Our least accurate measure in this case is our temperature, because it's only got one significant figure. Our mass has 3. Our specific heat is a constant, so we don't really worry about those because they actually go out to way more digits than we need to know. So we look only at the things that we measured. And so in this case, we need one significant figure. So how do we round this answer to one significant figure? Well, what's our first digit? Right, the 1. We look to the right. Can I round that up? No. And so then, in order to keep one significant figure, in this case I'm going to have to round down to 1,000 joules, because this number has 3 significant figures, and so now this one only has 1. Alright, so let's look at the second problem. Looking at the heat of a phase change. So we have a 25 gram piece of ice which undergoes melting to a liquid at 0 degrees Celsius. So how much heat energy did it take to do this? Alright, so we are melting, which means we have a phase change.